Hi everyone! Today let's talk about sessions 11.4, cross products. Let V and W be vectors. Let theta be the angle between them. The cross product V cross W is the vector that is uniquely characterized by the following geometric properties. So we know it's a vector, so we can talk about its magnitude and direction. So here, keep in mind, dot product is a scalar, so it's a number. Okay, and the cross product is a vector. It has direction. So this is a really, really big difference, okay? So keep this in mind. Okay, so let's look at the magnitude. The magnitude of V cross W equals the magnitude of V times the magnitude of W times sine theta. So what does that mean? Okay, so let this be theta. And let's build this right angle triangle by drawing a line that's perpendicular to the vector V. Okay, so we know this guy is the length of W. And then this guy, let's call it H. Okay, H is the opposite of the right angle triangle, right? So the opposite over the hypotenuse is sine theta. So that's why H equals the magnitude of W times sine theta. Okay, so magnitude of W times sine theta. And then this guy is magnitude of V. Now for a parallelogram, the height times the base, what does that give you? That gives us the area of the parallelogram, right? So area equals base times height, but the base is actually magnitude of V. The height is magnitude of W times sine theta. So it actually gives us the area of the parallelogram. Okay, so notice the different dot product. Okay, so dot product U dot V equals U V times cosine theta, and cross product is U cross V. The magnitude, okay, so we have some magnitude and times some direction. Okay, so the magnitude equals U V sine theta. Okay, so that's the magnitude. Now let's continue to look at its direction. So if V and W are not parallel, then V cross W is perpendicular to both V and W and points in the direction determined by the right-hand rule. If the fingers of the right hand curl from V to W, so let me try to draw here. So your thumb here, and then your fingers are here. If your fingers curl from V to W, then your thumbs points up, right? It points up from the paper. So then your thumb points in the direction of V cross W. Okay, so for example, for the vectors V and W in the figure, V cross W points up of the paper. Okay, so imagine this is your paper. Up, this is up. Okay, pointing out of the paper. And then W cross V, then we have like our hand is like, our right hand is like this, and then our thumb okay, this is our thumb. It goes down. Okay, so far so good, everybody. Okay, maybe you can draw a better picture than I do. I think I just draw a banana. No, a hand. Okay. So anyway, the geometric description gives us a characterization of the parallel vectors. So two vectors v and w are parallel if and only if the cross product equals 0. And don't forget the cross products. It is a vector. Okay, so the cross product, if you want to put 0, you mean the 0 vector. Okay, so because the magnitude of it is v w sine theta. If they are parallel, means theta equals 0 degrees and sine of 0 equals 0. So far so good, everybody? Okay, so besides the cross products, do you remember before we also talked about what happened if two vectors are parallel? So if and only if they are scalar multiple of each other, right? So they're scalar multiple of each other. Okay, so now we have learned like two conditions we can tell parallel. One, check whether they're scalar multiple of each other, or we can calculate the cross products and see whether the magnitude equals 0. Okay, but in general, I suggest to use scalar multiple because it's easier. Oh yeah, I also put it in the comments. So this fact is often useful when computing cross products, but if you're trying to check if two vectors are parallel, you should not waste time computing their cross products. Just remember the two vectors are parallel if one is scalar multiple of the other. It is easier to check this than computing a cross product. Yes. So today we will learn how to compute a cross product. It actually related to determinants. Okay. And it's much more work than computing a dot product. So now let's see what happens if we compute the cross products of the standard basis vector. Okay, so standard basis vector, we have, this is I, J, and K, right? So if we put our fingers, so let's see, I cross I, we know I and I, they're the same vector, they're parallel. So if the vectors are parallel, then we get the cross product is 0. Okay, and it's a 0 vector. It's not just a 0 number. Okay, it's not a 0 number, it's a 0 vector. And then what is J cross I? Okay, so let's look at this picture. Use your hand. Okay, your right hand. Yeah, everybody must use right hand. So put your fingers curve from the vector I to J, and then your thumbs goes in the K direction. So in this case, we know that I cross J will give us K. So I cross J will give us K, right? So I cross J will give us K. And actually, look at this picture. If you do J and K, so J and K will give you I, okay? So J and K will give you I. And K and I will give us J. So K and I will give us J. So far, so good, everybody? Okay, and then for the rest, you can see if we do the other direction, J and J cross I. So if you put your finger like curve from J to I, then you see the vector goes down. So goes down, then it means it's minus K. Okay, so let's see. This is minus K. Do I change different color? Oh, okay. So I want to change a different color so you can see it. So this is minus K. And KJ will give us minus I. So KJ will give us minus I. Okay, and ik give us minus j. So far, so good, everybody. Okay, I really wish I can I can see you in person, and then I can show you using my right hand how to point. Okay, so let's continue. Physical intuition. The cross product V cross W is often interpreted by the physicist as a torque, a vector that describes the tendency of a force to twist a body about an axis. The idea is that we can think of the vector V as a rigid bar pinned at its tail, and then the vector W as the force exerted at the head of V. Okay, so we have the bar right here is pinned at its tail, and then we have a force acting on the head of it. Okay, how do we trace it? Well, we want to measure the components that are perpendicular to V, because to trace it, you want to have this perpendicular component, then you can trace the bar onto this direction. In this case, is a counterclockwise direction. Okay, so the twisting tendency at the tail V is the length of V measures times the scalar projection of the force W perpendicular to V. Okay, so this is W, then this projection is W times. Okay, so in this case, we have this is theta, right? So this is theta. Well, it's the same as this guy is theta, right? Because remember, those are two parallel lines, and then those two angles are equal. And then what this guy is, so this guy is the opposite of it. So opposite over hypotenuse is sine theta. So this guy is the length of W times sine theta. Okay. So the twisting tendency is, we have the magnitude, the length of V times the scalar projection of the force perpendicular to V. So which is, in other words, the torque at the tail V has the magnitude equal to V times W, the length of W times sine theta. The direction of the torque vector is the direction in which the bolts at the tail of the V will move. So this is given by the right-hand rule, which is the usual rule when you use a wrench to adjust a bolt. Left loosey, right tighty. So can you imagine when you adjust a bolt? So when you twist it counterclockwise, then it's more loosey. If you twist it clockwise, it's more tighty. Okay, and so that's why the cross products we have the magnitude, the length of V times length of W times sine theta. And then based on this physical intuition of torque, it is not shocking that the cross product satisfies a lot of usual algebraic rules of multiplication with corresponding physical interpretation. The cross product satisfies the following algebraic rules. So for vectors u, v, w, and the scalar r, u cross v equals minus v cross u. So notice that it is not commutative. Okay, remember our dot products? Our dot product is commutative. However, the cross product is not commutative. Actually, when you change the order of it, the answer will be negative. Okay, the opposite direction. And then for the scalar multiple, we can still multiply the scalar by the first vector or the second vector or the cross product vector. Okay, so this is scalar multiple, it still holds, and the distributive law still holds. Okay, So it's not commutative, but it's distributive, and we also have the scalar multiplication types. Okay, next. Components formula. Using the table above with the standard basis together with some algebraic rules, we can obtain the following simple formula for the cross product. I don't think this is quite simple. Okay, so wow, you may ask, how can we memorize this? Yeah, it looks impossible to remember, but we can see how it fits the pattern when we evaluate the 3x3 matrix determinants. Okay. So if you have taken linear algebra, then you probably know how to calculate the determinants. If you haven't, it's okay. You know, all the math courses, one is, I would say Calc 3 and linear algebra and differential equation. No matter which course you take first, the first course will kind of help the second course. So maybe you haven't seen like these concepts before, but then you take Calc 3 and then you learn about it. The next course, when you take linear algebra differential equation, then you can have like more idea and more familiar with the concepts. Okay, or if you have taken linear algebra differential equation, that's good. So you're already familiar with these concepts. Okay, so the determinants of a matrix A is denoted both the absolute value of A and the determinant of A. So we have two notation. The formula for the determinants of a 2x2 matrix, a typo here, equals, so how to calculate 2x2 matrix? So AD minus BC. So you use cross multiply and then you put subtracts in the middle. Okay, so AD minus BC. So far so good, everybody? Okay. And the formula for the 3x3 determinants, okay, the determinants of a 3x3 matrix is, okay, so actually for a 3x3 matrix there are 6 ways to compute the determinants. Okay, so we can choose any column cofactor expansion, or we can choose any row cofactor expansion. Okay, so in this case, let me just teach you the easy just use one way. Use the first row cofactor expansion. Okay, how does it work? First, look at the first row, and then you're gonna assign some sign to it. So the 1 entry is always plus, and then it alternates the sign, plus, minus, plus. Okay, for example, how about the second row? Well, the first 1 entry is always plus, then this guy alternates to minus, this is plus, this is minus. Okay, so anyway, here we just need to learn the first row cofactor expansion. We don't need to use the other rows or other columns cofactor expansion. So I don't need to talk about like so. But if you're interested to learn more about it, feel free to come to see me. Okay, I'm happy to explain to you more. Okay, so and then after we assign the sign to it, then the determinants is plus times A1, and then we have the determinants of the submatrix by deleting the first column and the first row, okay, which is this guy. So you put the determinant of this guy, the submatrix here. Okay, this guy is also called the minor. Okay, and then next we have this sign minus, right? That's why we subtract times A2. And then we multiply by the determinants of the submatrix by deleting the first row and the second column. So that's B1, C1, B3, C3. So right here. Okay? And then we have plus A3 and then times the minor. The minor is the determinant of the submatrix by deleting the first row and the last column, which is this guy. So that's why we have the determinants of the 2 by 2 matrix B1, C1, B2, C2. So far so good, everybody? Okay. And then you know when we continue, this guy is just cross multiply but subtract. So B2 minus B2 C3 minus C2 B3, and this is A2 and then cross multiply but subtract. B1 C3 minus C1 B3, and then we have A3 B1 C2 minus C1 B2. Okay, and so we can distribute and then calculate the numbers and add them together. So far so good. Okay, now the cross products. So the cross products V1, V2, V3 cross W1, W2, W3. The first row we write down the unit vector, okay, the IJK unit vector, basis vector. For the second row, we write down the components of V. The third row, we write down the components of W. Okay. And then we compute the determinant. So positive, negative, positive. So plus I times determinant of the submatrix V2, W2, V3, W3, and then minus J, okay, minus J, and then the determinant of V1, W1, V3, W3, and then plus K, and then times the determinant of the submatrix V1, W1, V2, W2. Okay, and then that's why you have this guy is cross multiply V2 W3 minus V3 W2 I minus V1 W3 W1 V3 J plus V1 W2 minus V2 W1 K. And then you will realize, well, this guy is the same as our formula. Okay? And I would prefer to use this determinant approach. I don't memorize the formula. I just like imagine what's the procedure of calculating the determinants, and then we can figure out the cross products. Okay, so we have talked a lot. Let's do some example. Yes. I know you have been waiting the example for a long time, right? Because we keep talking about the meaning, the concepts, the definitions, the theories, but we don't have a chance to do examples. But now, because I have to explain you the rule how to compute, and it's quite a little bit complicated. But after we learn the rule, we can then work on the problems. Okay, thank you for being patient. Okay, now let's compute the cross products. So what do? Remember, it's determinants. First row, I, J, K. Second row is the first vector, 2, minus 4, 1. And then the last row is the second vector, minus 3, 2, and 5. Alright, so what is that? Okay, that is, so this is plus, minus, plus. So we have I times submatrix of, so the determinant of the submatrix by deleting the first row and the first column. So minus 4, 2, 1, and 5. Then minus J, we have the submatrix by deleting the first row and the second column. So we have 2, negative 3, 1, 5. And then for k, we delete the first row and the last column, so we have plus k and times the determinants of 2 minus 3 minus 4 and 2. Okay, what is that? Cross multiply. Minus 4 times 5 minus 2 times 1 minus j 2 times 5 minus 3 times 1 plus k 2 times 2 minus negative 3 times negative 4. Alright, so that is minus 20 minus 2. That is 10 plus 3. That is k times 4 minus 12. Okay, so this is minus 22i and then minus 13j and then minus 8k. So if we want to put it in the components form, this is minus 22, minus 13, and minus 8. So far, so good, everybody. Okay, do you have the same answer? Okay, alright. Let's continue in video part B, then we can do more examples. See you soon.